Hello, I'm Simon Davidmann, CEO of Imperas, and in this talk with my colleague Lee Moore, we're going to talk about open source RISC-V cores and their development with industrial strength verification. I'm going to start with an introduction to open hardware. I'll then introduce the open hardware core-v-verif testbench environment and discuss its evolution and where Imperas are involved. I'm then going to hand over to Lee, who's going to walk through the environment as a case study into industrial strength verification. And after Lee's demonstration, I'll summarize the components needed in DV and introduce a new verification standard. Open Hardware Group's a global non-profit incorporated in Ottawa, Canada, and was founded by Rick O'Connor. Rick was the founding executive director of the RISC-V Foundation. Open Hardware was founded in 2019 and currently has over 80 companies and more than 10 partners like Imperas involved with it. Open Hardware develops quality open source cores, and the originals came from the Pulp platform group in ETH Zurich. There are currently 9 under development, 32 and 64-bit, ranging from controllers to application processors running virtual memory and Linux. The focus is the open source cores, but with industrial quality verification, and that's where Imperas is involved. We partner with Open Hardware, providing the golden reference models and the DV technology. I'm now going to talk a little bit about the evolution of the open hardware test bench called core-v-verif. There are many cores in open hardware, and the test bench needs to work with each of them. The test bench is available as open source on GitHub, and the key thing is that it provides industrial quality components and verification. For example, it uses System Verilog UVM, and it runs with all the commercial System Verilog compatible simulators. It provides the components that provide complete code coverage, comprehensive functional coverage, and there are detailed verification plans for each core. And being open source, you can download it, use it as is with your own open hardware cores, and of course you can modify them. And then you can reuse the test bench and test and be confident that you've not broken anything. Or of course you can modify it for your own cores or use just parts of it in your own test benches. So it's industrial quality verification for open source cores. The first version of core-v-verif testbench was built for the first core, the CV32E40P, and Imperas provides the reference model. We work with the open hardware team to develop both the synchronous asynchronous lockstep compare capabilities in the test bench. That means for interrupts and debug events, we could randomly create them and include properties and assertions and functional coverage to ensure that they were fully exercised, all the time running in this lockstep compare mode, comparing the RTL DUT with the Imperas reference model. This was simulated both with directed and constrained random tests, and of course the Imperas reference model was encapsulated in System Verilog. And there was a big challenge in how to evolve this test bench to handle the different cores that were on the horizon. In 2021, we evolved the test bench to make use of the evolving standards like RBVI to allow ease of changing the RTL core and the reference model. RBVI, the RISC-V verification interface, is covered in a later slide, the key thing being that the components can plug and play and be replaced without completely rewriting everything, making it much easier to get a new core up and running and tested. Now, Lee Moore will give us a demonstration.
Thanks, Simon. I want to quickly recap on what is encapsulated within the Imperas RISC-V envelope model and why. The model itself has to be capable of supporting all of the ISA subsets, including versions which may not yet be ratified. We have customers who are already designing SoCs using the draft proposals of some of the subsets in order to be first to market with their products. This does not negate from their ability to iterate their designs later once the subsets are ratified, but it does enable early market capture. Further to the subset versions, there are many architecture choices open to a specific implementation. A very simple example would be whether to support misaligned load and store accesses. This is an implementation choice. The Imperas RISC-V envelope model currently provides approximately 200 configuration options. This gives an indication of just how configurable the RISC-V architecture is, but more importantly, it's imperative that an architectural model must be capable of implementing those option combinations in a behaviorally correct manner in order to act as an accurate reference. It is essential that the reference model is easily capable of allowing its internal architectural state representation to be accessed for analysis and comparison to the microarchitectural implementation. The Imperas RISC-V reference model exposes all of the program of visible state, for example, the standard set of GPR, FPR, vector, CSR, both custom and standard, and debug registers. And additionally, non-program of visible state can also be provided through the same interface if desired to further enhance the microarchitecture comparisons. As part of the Imperas suite of simulation tools, the end user is able to leverage all of these capabilities as part of their simulation framework, including detailed tracing of instructions, registers, operation modes and nets, high-level views of execution such as CPU operation or tracing or even OS tracing, interactive multi-heart debug using graphical or command line analysis, verification analysis profiling tools for software analysis, performance analysis, coverage analysis and also assertions. All of these capabilities and techniques are available as part of this reference model framework. The integration of the Imperas RISC-V reference model into the OpenHW UVM framework is captured on this slide. Applications are compiled and loaded into both the RTL and the reference model memory. The two implementations are then run in lockstep on an event-by-event basis, and events in this environment are denoted by either program exceptions, both precise and imprecise, or instruction execution retirement. As these events are architecturally visible, they form the basis of the UVM scoreboarding comparisons of state to ensure correct behavior of the RTL to the architectural reference representation. Let's now execute the simplest Hello World application in the UVM step and compare environment. Here we see the elaboration and the execution of the application in our environment, and on each architecturally visible event we perform a comparison in the UVM scoreboarding. If all is well, we should have a silent output. If not, then it's going to report an issue. And as you can see here, we've had a report of a GPR mismatch, gives us the program counter, the hardware register involved and the values involved. Well, the first thing I'd do at this point, I think, would be turn on some additional diagnostics such as tracing. So I'm going to do that. I'm going to turn on the tracing, and I'm going to rerun the application running inside of the platform. And this should then give us a lead up to the event where we had the miscomparison between the architectural and the RTL model. So again, let's have a look back here. So we can see the last instruction to execute was a multiply instruction, and it should have written a new value of 138 to register S1, but the RTL has not taken that value. It's still got the previous value in there. And if I go and have a look at the RTL associated with this instruction, well, you know, like all good demos, it's deliberately been corrupted. So what I'm going to do is I'm going to take out my corruption in the RTL. I'll save that file, and then I'm going to rerun. What I'll also do, actually, I'm going to turn off the tracing because we may be swamped with too much information. What I really want to see is back to just the UVM error reporting and the output from the application itself. So it's a Hello World program. It should print Hello World to the standard output, and hopefully we don't get any UVM miscompares whilst this is executing, and we should get a status at the end telling us that it's passed and met all of the comparisons. So there we see the Hello World being printed out, and just as we'd hoped, we get a passed at the end of the simulation. A lightning talk clearly can't do justice to the capabilities we've been discussing here today, but hopefully you've had a glimpse into the types of tools and technologies we have available to us, including things like traditional waveform views, software debuggers. And in fact, you know, I could show you here where we are executing an application, and you can see the interaction between both the traditional waveform view and what we have inside of our debugger. If I go into instruction stepping mode, and you know, I start stepping through, you see that as we execute the instructions, then our waveform display is also updating down the bottom, and we have complete visibility of everything within our platform here. So we can see all of the software views of registers in addition to the hardware views of registers, which clearly represent the values held in the hardware registers as opposed to the register values on the stack. So hopefully that's given you a good introduction of what we have available here. Thanks for listening, and let's go back to Simon.
Okay, thanks, Lee. Now, there are really 5 main components in a really good lockstep compared test bench. And on the right of the diagram is the reference model subsystem, which includes the model that the DUT is being compared to and the appropriate synchronization capabilities and various other components that connects up to the test bench with an interface. And for Imperas, we use the new RBVI API interface The test bench in the middle connects the DUT and the reference subsystem, controls the loading of programs and the stepping of the other components. And with the use of the Imperas DB solution, the test bench becomes really quite simple and easy to create. And one thing that's very important to note is that the Imperas DB products work not only with just the system Verilog test benches, they also work with C++ test benches. So if you've got a verilator, for example, for your core, then you can use the Imperas DB products with your verilated core, and the Imperas DB technologies get your full lockstep compare verification with Imperas and Verilator. As I mentioned, to make more processes DB reusable, we need to adopt standard interface for connecting components in our DB test benches. And that's where RBVI, the RISC-V verification interface, comes in. It's available as an open standard. It comes in 3 sections. And for more information, please go and look at the GitHub. So, in summary, RISC-V processor DB requires a high-quality approach, and the Imperas lockstep compare technology provides an industrial-grade solution. So, to save everyone reinventing the wheel, we have to develop verification component standards, and this helps ease of use and reuse. Now, we've talked about open hardware, core-v-verif, and high-quality open-source lockstep compare test bench that you can download and use with your open hardware cores and also your modified ones. So if you're developing cores, you can use that test bench. Now, we also demonstrate and talk about how the Imperas DB technology works for industrial grade verification. And so you can see why our solutions are used by many of the leaders in the RISC-V processor development arena. Thank you.